Okay, in this video, we will learn about the atomic number, the mass number, this is a nuclear symbol, and also we'll learn about isotopes. Okay. So in the last video, you learned that atoms were made up of electrons, protons, and neutrons. And it's the protons and neutrons that are in the nucleus, and the electrons are on the outside of the nucleus. Protons are positively charged and electrons are negatively charged. So for a nuclear symbol here, so this is how we will write an isotope, or to write a particular type of element, right? This is carbon 12, right? So carbon is the element symbol, the C. 12 is up here in the upper left-hand corner. That is known as the mass number. And the mass number is the number of protons plus the number of neutrons, right, for that particular atom. And over here in the lower left-hand side, that is the Z, that is the atomic number, which is your number of protons. So your number of protons are written on the lower left, and in the upper left is the mass number, which is the protons and the neutrons that are found in the nucleus. So when you look at a periodic table, though, like for instance, if we're looking here at carbon, you can zoom in on carbon right here. And we see the 6, right? Right, that is the atomic number. That tells you the number of protons. What you don't see is the mass number. What you're looking at here, this 12.01, that is a relative atomic mass. So that is the average of all the different types of carbons we know in the universe. So looking at your element symbol, right, you don't see that 12.01, you just see 12. And that's for a very specific isotope. Okay, so a carbon can exist at many different types of isotopes, and what you're seeing there on the periodic table is, I believe, your book calls it the relative atomic mass. Yeah. Okay. So that right there is the relative atomic mass. So isotopes of an element, there we go, will have the same number of protons because they are, right, that particular element. So that particular element always has the same number of protons. So let's go back here. So you see, if you're an element carbon, right, you always have 6 protons, right? You change your proton number. So let's say we add a proton to 7. Well, you just changed your element. So now you are nitrogen. If you take a proton away, and then you're 5 protons, and you've changed the element. You are now boron. So the number of protons tells the identity of the element. And that's how the periodic table here is arranged. It's arranged by proton number. So an isotope of an element will have the same number of protons, the same Z number, atomic number. But what differs for isotopes is their number of neutrons. So they have a different mass number. Okay, so looking at here, the isotopes of hydrogen. Okay, so hydrogen, we can see they all should have a 1 for their atomic number. And so again, looking at the periodic table, hydrogen is 1. Okay. So the atomic number is the same because they're all hydrogen atoms. Hydrogen 1 has just a proton, right? So the mass is 1. There are no neutrons. Hydrogen 2 has a proton and a neutron, so the mass number is 2. Hydrogen 3, right, known as tritium, it has 1 proton and 2 neutrons, so that's the mass number of 3. And it is tritium that is radioactive, and you'll sometimes see that they still use it in watches. So because it's radioactive, it will react with the phosphor and light up the screen. So for these glowing, I guess they're not glow in the dark, but they're phosphorescent screens that are in the dark, they're always glowing. Okay, so an isotope of an element will have the same number of protons, but different number of neutrons. Okay. And this is why you'll see here for hydrogen, right? You see that the relative atomic mass is not 1 exactly, it's higher than 1 because you have these other isotopes. Even though hydrogen 1 is the most abundant, you still have some hydrogen 2 and hydrogen 3, right, in the universe, and that's making that relative mass bump up a little bit. Okay, so let's take a look at the isotopes of carbon. Okay, so if we have carbon 12, right, you would write that as carbon 12. Right, carbon 13 and carbon 14. Okay. So these are isotopes of carbon. Carbon 12 is the most abundant. That's why the relative atomic mass is 12.01, but there's some of these other isotopes around. Carbon 14 is radioactive, and this is what we used for archaeological dating, so carbon 14 dating. All right, so let's look at these 3 as an example. And if I asked what's your number of protons, right, for each one, right? You would look at the periodic table and you would see that the atomic number is 6, and so they should each have 6 protons. It's the neutrons that are different, right, for these 3 isotopes. So for carbon 12, remember this number here, right, is the sum of your protons plus your neutrons, right? That's the mass number. So how many neutrons in carbon 12? Well, that's 6. They should add up to 12. For carbon 13, right, we can't change the protons. They have to be 6 because it's carbon. So we have 7 neutrons. And again, for carbon 14, since it's carbon, it must be 6 protons. So there are 8 neutrons. Okay, so again, just pointing out here that relative atomic mass is a little higher than 12 because of these other isotopes of carbon. Okay, so let's do a practice problem. It says, write the nuclear symbol for the following element. Okay, so go ahead and you can pause the video and try it on your own. Okay, so let's see, let's count our protons. And we have 1, we have 2, we have 3 protons. Okay, so let's make a note of that. Protons equal 3. You look at your periodic table, and we're looking for 3, right? That has 3 protons, so it is lithium. Okay, so I know that my element symbol is Li for lithium. I could put the 3 there, but it's not always listed because it's obviously 3 because it's lithium. And oh, here it's actually expanded for us. We have 1, 2, 3, 4 neutrons. So for our mass number, right, we would have 3 protons plus 4 neutrons. So it's lithium 7. And this would be the nuclear symbol, right, that you would write. Okay. You could, it's also written as lithium-7. Okay, a couple more practice problems. Determine the number of protons and neutrons in each of the following isotopes. So you can go ahead and pause it. Okay, so here we have chlorine. It's telling us it's element 17, which has 17 protons. Okay, so protons equal 17. How many neutrons? Well, we know that 35, right, is the total of protons and neutrons. Subtract out the protons and you are left with 18 neutrons. Okay. Gold, okay, well, we didn't get the neutron number, but you could look at a periodic table and you would find that the atomic number of gold is 79. Okay. So that tells you your number of protons. So remember, that's not always written, but if it was written, it would be right there, right? That's the atomic number. And then you would subtract 79 from 198 to get 119, right? Is your number of neutrons. Okay. So just a note about the subatomic particles. The importance of each of them. Remember, your protons and neutrons, right, are located in the center, right? They're the nucleus. They make up most of the mass of the atom, okay? Because the electrons are negligible, right? They're very, very small. And it is the number of protons that determines the element. And so that's what you would find as the atomic number on the periodic table. And the analogy is, if an atom was a football stadium, the nucleus would be a marble on the 50-yard line. So right here in the very center of this little marble would be your protons and your neutrons. The electrons are located around the nucleus. As we'll learn in later chapters, they're found in orbitals, and they make up most of the size of the atom. And since the electrons are on the outside of the atom, that's what determines the reactivity of that atom, because it's the electrons that see the outside world. They're the ones interacting with other atoms. And so of the football stadium, the rest of the football stadium, right, is where the electrons are flying around in orbitals. Right, they're moving at 1% the speed of light. They're moving so fast that if you tried to enter the stadium, you wouldn't be able to enter it. Okay, because the electrons are moving quickly around the outsides of the atoms. Okay, so keep in mind, the protons and neutrons, they make up most of the mass, very small nucleus in the center. The electrons, although negligible in mass, they make up the size. They fill the space on the outside of the atom, and they're the ones that are interacting with other atoms.